Well, hi there, everybody. Today we're going to start our class by going over the homework sheet called Group Work 8X. And as you can see, I have it up here on the screen. So here we go. All right. I have blown the file up to a very nice large size so everyone can see it very easily, and we can work on it very easily. So here we go. So it says, for number one, write the exact value of the golden ratio. Well, you know what that is, and if you don't know what that is, you're going to want to know before the next test. But at any rate, the exact value of the golden ratio, or phi, is equal to 1 plus the square root of phi all over 2. Remember, that is an exact value because of the fact it has a radical in it. And the radical is not approximated, so you know that this is the exact value. Then it says in number 2, to write the correct value of the golden ratio, correct to 6 decimal places. So if you don't know that or have not memorized that, you don't have to. You can simply go on your calculator, take the square root of 5 here, add 1 to it, get that answer, and divide it by 2, and it will give you this 1.618034. It comes out 339 on the calculator, but you just take the 39, and make it a 4 to make it 6 decimal places. It says in number 3 to list the first 20 prime numbers. Well, if you don't have a prime number list sheet in front of you, let's just kind of go through it together the way we'd do it if we didn't have a sheet to cheat off of. Well, you know the lowest prime number is 2, right? Then next is 3. The rest of the prime numbers are odd, right? But not all odd natural numbers are prime, but that you know that, but let's continue. So here's 5, okay, 7, 9's divisible by 3, no good. So there is the next one, which is 11. Now I'm going to leave a little space between these, so I know I'm up to 20 of them. So there's the first 5. So the next 5 would be 13. All right, 15's no good. It's divisible by 5, right? So 17, 19, 21's no good because it's divisible by 7 and 3. So we have to go to 23. 24 is no good because it's even. 25 is no good because it's divisible by 5. 26 is divisible by 2. 27 is divisible by 3. 28 is divisible by 2. So the next one is 29. Okay, so now we've got 10 of them. We're halfway there. So let's keep going. Well, next is 31. 33 is no good. All right. 35 is no good because it's divisible by 5. So the next one will be 37. A lot of people sometimes think that 33 is, that 39 is a prime number, but it's not because it is divisible by 3. So the next number we have to go to is 41. So let's see, 1, 2, 3, 4, 5. I had 5 more there, so I have only what, 3, so I need 2 more. So to make my 15th one, 43, 45 is divisible by 5. So next one is 47. Okay, so here are 5 to here. Here are 5 of them to here. Here are 5 more, so I need the last 5. So 49's no good, right? How about 51? A lot of people think 51's prime. It just kind of smells like it's prime. But guess what? 5 plus 1 is 6. 6 is divisible by 3, so is 51. So 51's no good. So 53, 55 is divisible by 5, no good. So 57 is our next one. All right, well, wait a minute. 57. 5 and 7 adds up to what? 12, doesn't it? Which is divisible by 3. So 57 is an incorrect choice. Let me go back to 53. 55 is no good. 56 is no good. 57 is no good. All right, so our next one is going to be what? 59. All right. Our next one will be 61. 63 is divisible by 3. 65 is divisible by 5. 67 is our next one. All right. And of course, our next one appears to be what? It appears it's going to be probably 71. Okay. Let's see if I've got 25, 10, 15, 20 of them. So it looks like I have the first 20. Almost messed up there on that one, didn't I? So 57 was not right because it is divisible by 3. Okay, so there we go. All right, number 4. Circle the numbers in this list which are divisible by 3. Well, these two add up to 15, these two digits, so we know it's divisible by 3. 29, they only add up to 11, no good. This adds up to 12, which is divisible by 3, so is 48. This adds up to 9, so that's got to be divisible by 3. This adds up to 13, that's no good. 493, well, that adds up to 16, so that's no good. 707, those two digits, 7 and 7, add up to 14, so that's not divisible by 3. I think you can see that this one is because it adds up to a total of 18, the 3 digits. Okay, the next one, it's 11 and 12, which I believe is 23, no good. All right, how about the next one? Let's see, 13 and 8 is 21, and 7 is 28. That doesn't look like it's any good either. How about this one? Well, there's a 7, there's a 7, and there's a 7. 3 sevens is 21. 21 is divisible by 3. So this number is also divisible by 3. And of course, you know that you could just take a calculator on these larger numbers and just divide by 3 each time. If it comes out even with no what I call junk on the end, right? Junk is when you get a decimal answer behind, or it doesn't come out even. You get some kind of decimal left over. I call that junk. If you get junk, you can, of course, realize that it's not divisible by that number. All right, well, let's go to our next question. See if I can get this to come down a little bit. Okay, write the correct prime factorization for 99. Well, for 99, it's very simple. I simply take it. I know it's divisible by 3. I get 33, right? And of course, I know 33 is divisible by 3, and I obtain the prime number 11. So the prime factorization here is simply what? 3 times 3 times 11. For 51, of course, we went over that one a little while ago. We noted that 5 plus 1 adds up to 6. So we know that 51 is divisible by 3, and it goes 17 times. So this prime factorization for 51 is 3 times 17. And looking at 7, you can tell that its correct prime factorization can be found by dividing 303 by 3. All right, and that's 101. I'm pretty sure 101 is a prime number. So what we're going to do is write the answer down as 3 times 101. Okay, so there, we have finished that group of questions. Let's move on. You're supposed to use these tables, all right, to do the next set of questions, okay? So we have the Luca numbers listed here and the Fibonacci's. You are to write the Luca number 1006 as the sum of non-consecutive Lucas. Okay, or right, being a natural number, I'm sorry, 1006 is a sum of non-consecutive Lucas. So let's see, I'm going to start by writing down 1006, and I'm going to look for the closest Luca number, if you recall, to it, all right, which is smaller than it, not larger, but smaller. Well, it appears to be 843, right? Okay, something has to be added to 843 to get 1006. I'm going back here to my adding machine, take 1006. I'm going to take 843 from it. And when I do, I get 163. All right, so 163. Well, I'm finished with this problem if 163 is a Luca number. Unfortunately, it appears that it is not. So I keep going, 1006, 843, let me make a little better 8 there, plus, now what is the closest Luca that's smaller than 163? Well, it appears it's 123. How much did I miss 163 by? It appears it's 40, right? Is 40 a Luca number? No, it is not. So I continue. So I go to 1006 equals 843 plus 123. And my closest Luca that's smaller than 40 is 29. How much am I missing 40 by? I'm missing it by 11, right? So is 11 a Luca number? Yes, it is. So guess what? Here is my answer. So, and you'll notice if you go back and you look at the table and you check out where those numbers are located, 843, 123, 29, and 11, none of them are next to each other. So you know that you have done the problem correctly. Okay, let's go to our next question. Next question asks us, all right, to show that this expression is a true statement when n is equal to 16. Now you should have your Luca table, or excuse me, your Fibonacci table right there in front of you, all right? I've covered it up by sliding the screen up a little bit too much, but I'm just going to go right here with it. All right, so what am I going to get? I'm going to get 2 times f sub what? F sub 16. If I subtract from that, f sub what? Putting the 16 in the subscript, I get f sub 14, right? And that is supposed to come out to be f sub what? Well, n plus 1 would be f sub 17. So I look on my table for Fibonacci number 16. Fibonacci number 16, of course, is 987. From it, I'm going to subtract Fibonacci 14, which is 377. And according to this, I'm hopefully going to get Fibonacci number 17, which is 1597. So if I go to a calculator and I take 987 and multiply it times 2, I get 1974. I'm going to put that here, 1974. And from it, I have to subtract 377. Do I indeed get 1597? Well, so if I take 1974 and subtract 377, I do indeed get 1597. So 1597 does come out equal to 1597. So it checks out. QED, baby, right? Quite enough done. You can give me an attitude, that symbol, remember, stands for quite enough done. It's actually Latin for something else, but just remember quite enough done. And you have shown that those two are indeed true. All right, let's go to the next one. All right, we are now going to determine if I take Luca number n plus 1, add to it Luca number n minus 2, will I get twice Luca number n when n is 17? So I will fill it in first, okay, with the subscripts. So if I take Luca, 17 plus 1 would be Luca 18. And if I add to it, Luca what? Well, let's see, 17 minus 2 is 15. So if I add to it Luca 15, is that the same thing as twice Luca what? Luca 17. Well, looking at my table, Luca 18, okay, Luca 18 is 3571. Luca 15 is 843. If I add those together, will I get twice Luca 17? And of course, Luca 17 is 1364. Well, the first thing I'm going to do is add 3571, and to it I'm going to add 843. When I do, I get 4414. Okay. All right. Now, if I double 1364, I don't get the right answer, do I? Something is wrong. I got 2728. So let me write this down, 2728. What did I do wrong here? It appears I added these two together, right? That's what I was supposed to do. Well, let's see. Luca 18, I'm checking it out, it's 3571. Luca 15 is 843. Oh, Luca 17 isn't 1364, is it? It is 2207. All right. So now, if I double 2207, you can see I'm going to get 4414, right? All right, so this is finally checked out. QED, we've done enough to show it, okay? Now, even your math teachers screw up every now and then. Now, you probably noticed that when I made this PDF file, I made it backwards. What I mean is I put page 2 first and page 1 second, but that's all right. I mean, it's not going to kill us. So let's go. I figured out, I'll just leave it that way. So I'm going to go back up now to page 2, hopefully here. All right, which composite number has more prime numbers in its prime factorization? 11,550 or 44,590? Well, let's try it out and see. Okay, so let's go over here. Let's take 11,550 and let's start successively dividing it by primes. You know 5 will go into it. So I'm going to use my scientific calculator I have here close by. So if I take 11550, and if I divide that by 5, I obtain 2310. Now, I'm finished if 2310 is prime, but of course it isn't. It ends in 0, so you know it's divisible by 5. It's also divisible by 2, but let's divide by the larger number. It seems to go a little faster that way. So I'm going to take 2310. I'm going to divide it by 5. When I do, I get 462. Well, 462 is an even number, so I know I can divide it by 2. So I get 231. Well, 231 is not divisible by 2, but it is divisible by 3. And when you divide by 3, I believe you get 77. And of course, 77 is divisible by 7. So now my top number, 11, is a prime. So it appears that 11 by 50 has a prime factorization, putting them in order of 2 times 3 times 5 times 5 times 7 times 11. So it appears it has 6 members in its prime factorization. Well, let's try 44,590. Okay, well, it's divisible. That's a 9, right? So that is divisible by 5. So let's start that out. So let me go over here to my calculator. 44,590 divided by 5 is 8918. Now, 8019 is definitely even, so I'm going to divide it by 2. So if I hit divided by 2, I get 4459. Now, let's add the digits together on 4459, and let's see if maybe it's divisible by 3. 4 and 4 is 8, 8 and 5 is 13, and 13 and 9 is 22. Yuck, that's not very helpful, is it? So this is not a very user-friendly number here. So what are we going to do? Well, what we have to do is play with this number and make sure that we find its prime factorization. And we're going to be working on that today in class because I want you to be able to work with huge numbers such as the ones you've just seen. I'm just rechecking my divisions here. All right, wait a minute. I wrote something down wrong here. No, I didn't either. It is 4459. Well, let's see. We haven't developed a system really yet to test 4459 to find out if it's prime or composite. We will develop that system today, all right, in class. But so, gee, what are we going to do? Well, we just got to keep dividing by primes. So it appears that 5 won't go into it. 3 will definitely not go into it. So let's try 7. So you just take your calculator and you take 4459 and you hit divided by 7. Ooh, you get 637. Well, that worked out all right. So let's see how that works. All right, so dividing by 7, I get 637. Now, wait a minute. Is 637 a prime number? I don't know. As I said, today we're going to develop a system to use to be able to check that. Well, 5, 2, and 7 definitely cannot divide, 5 and 2 definitely cannot divide into 637 because they would have divided into 4459. So let's try 7 again. So if I hit divided by 7, ooh, I got another answer, all right, that came out even. So by luck, if I divide by 7, I get 91. Boy, 91 sure smells like it could be prime, right? Well, is it? I don't know. Let's just, for the heck of it, try dividing it by 7. When you do, all right, it goes exactly 13 times. Most people think 91's prime, but it isn't, okay? It is divisible by 7. Well, 13's prime. So guess what? We just obtained that this answer is 44,590, its prime factorization, putting them in order, is 2 times 5 times 7 times 7. All right, let's see. 2 times 5 times 7. Ooh, what is this supposed to be? I don't know. I can't read it, so let me erase it. Let me get rid of that. Okay, let me go back to my draw tool. So 5 times 7 times 7. Oh, there's 3 sevens in it, right? Times 13. Okay. I could have used exponents also, right, to make this a little shorter, but I didn't use exponents in my final answers. All right. So which of these two numbers has more prime numbers in their prime factorizations? Neither one. They have the same number, right? Absolutely the same number, all right, as we have shown. Q, E, D. Quite enough done. We've shown it. Okay, let's go on. How many folds? Okay, trying to get this sheet down a little bit here. How many folds of a very large sheet of paper must be accomplished to surpass the height of 5 feet? Well, as you know, I'm going to have to get 5 feet into sheets of paper. So I'm going to start with 5 feet using dimensional analysis. I'm going to first get it down to inches, right? I know the 12 inches go on top because I want feet to cancel, right? So feet is on top here, so it's got to be on the bottom there. That would give me the answer in inches. Well, do you recall what the conversion factor is for sheets of paper of thickness and inches? Well, if you recall, for every 1 inch of thickness you have, if you stack sheets of paper on top of each other, there are 250 sheets per every 1 inch. Now, if I multiply this out, I will do 5 times 12, of course, which is 60. And I will do 60 times 250, which is 15,000 sheets of paper thick. Now, how many times would I have to fold a single sheet of paper to either equal 15,000 sheets or surpass it? Well, I'm looking for a power of 2, right? Because every time you fold a sheet of paper in half, you double its thickness, right? So I always usually start with maybe 2 to the 10th, just to give me a starting point. So if I go to my calculator and I do 2 caret 10, I get 1,024. Well, that's not near enough, right? All right, so let's try, why don't we try 2 to the 15th? So if we do 2 to the 15th power, what do we get? 2 caret 15 would give us 32,768 sheets. That's too much, but it's just about twice as much, right? Remember, each time we double, so if it's at 32,000, if you take half of 32,000, that's around 16,000, right? 16,000 something. So if we check out 2 to the 14th on our calculator, 2 caret 14, we get 16,384 sheets, all right? And of course, you know, if we cut that in half, it'd only be about 8,100 sheets, so that wouldn't be enough. So what's the answer to this question? The answer is, how many folds is it? It is what? 14 folds. Remember, when you take the big test that's going to be coming up soon, you've got to answer the question that's been asked. So be very careful on that. All right, let's go on. If there are 5 girls and 8 boys, I'll put over here 5 girls, 8 boys, in a particular class, and they all write their names on a 3x5 card, and then they place their cards in a small box. How many cards must the teacher draw the box without looking to guarantee that 2 cards drawn from the box will be names of girls? Gee, well, let's think about that. Probably wouldn't happen, but is it possible the teacher could keep reaching into the box and by some miracle pull out all the boys' names first? That could happen, right? And we want to guarantee that by the time she's done drawing, she has 2 cards that have girls' names on them. So she could actually draw 8 boy cards first. Then she'd have to draw how many more cards to make sure she had 2 girls? 2 more. So if she draws out 10 cards, right, she definitely will have to have 2 girl named cards, right? So the answer to this first question is 10 cards. How many cards would she have to draw out? So it'll consist of 1 boy's name and 1 girl's name. Well, this is crazy again, right? If she drew out all the girls' cards first, that'd be 3. Then the 4th card she would draw would be a boy's card, right? So that way, if the girls all came out first, I'm sorry, I said that wrong. If she drew out the girl cards first, there would be 5 cards she would have drawn. She'd have to draw 1 more to get a boy card. So then she would have drawn 6 cards, right? But wait a minute. What if she drew all the boys' cards first and then drew a girl card afterwards? That's what? 9 cards. So if she draws out 9 cards, she definitely is going to have 1 boy's name and 1 girl's name, right? So the answer to this is 9 cards. 2 cards drawn will be names of students of the same sex. Okay? So she either can get 2 girl cards or 2 boy cards. Doesn't make any difference which, right? They have to be the same sex. Well, if she drew a boy first, boy's card first, and a second boy's card, she's done. But what if she drew a boy's card first and then drew a girl's card next? She draws 2 cards out and they're both boy cards. She's good. She's got 2 cards of the same sex. Same thing if she draws 2 girl cards out. But what happens if she draws a boy card and then in the second draw she draws a girl card? What has to happen on the next draw? It's either going to be a boy or girl, right? So to absolutely guarantee that she will get, okay, 1 card of each sex, she is going to have to draw 3 cards. How many cards would she have to draw out to absolutely guarantee that 2 students' cards drawn were born in the same month of any particular year? Same month. Well, we know there's 12 months in a year, right? It's possible that she could draw, okay, 12 cards out of this box. And every single card she drew, whether it was a boy or a girl, would have a different birth month. Because there are 12 different birth months to pick from, right? But what definitely has to happen on draw number 13? She's got to have a duplication, right? Remember, this is a principle known as the PHP, right? PHP, baby, pigeonhole principle. Okay. All right. Duplication would have to occur when? On the 13th card. Definitely. So she has to draw 13 cards. That way she knows there has to be at least one duplication. Now there's probably more in there, but to guarantee it, she'd have to draw all 13 cards out. Okay? All right, a little different question, huh? All right, let's go on. If you and your best friend each have 20 bucks right now, how much money must you give to your friend so that she will have 7 times as much money on her than what you have? So here's you. Here is your friend. You both start with 20 bucks. Well, what if I gave her 5? She'd have 5 more. Whoop. So now I would have 15 and my friend would have 25. That certainly isn't, $25 isn't 7 times $15. Why don't we just keep going by 5s? What if we did another 5? So I'm going to write it like this, minus 5 more. So now we're at minus 10, right? If we have subtracted $10 from me, I have 10 bucks. She has what? She has 30, right? That's 3 times as much. I want it to be 7 times as much. Well, why don't we just go another 5 bucks? If we go another 5, we're subtracting $15 total. So now I'm down to what? 5 bucks. Okay. And what is she up to? 35 bucks. Whoa, baby. She has 7 times as much money as I do right now, right? So if I give her 15 bucks, that takes me down to $5. If I add $15 to her $20, that takes her up to 35. So this is me, and this is the friend. That's 7 times as much, right? Times 7. So that's the answer. You have to give her $15. All right, the last 2 questions on here involve the Fibonacci's and Lucas. And what I suggest you do, okay, is use your table that's on, the, I believe, the other side of the sheet, all right, and work these values out. Now, you got to be careful. I've said let n be 6 each time. I'm going to write that over here. N equals 6. So let's put the subscripts in there correctly. Question A would say what? F sub what? 4. But I'm going to square that subscript. Then I'm going to take the answer to the Fibonacci number that I get after I square the subscript and take it to the 6th power. So wait a minute, now let me write this down a little better. F16, I'm going to take that to the 6th power. Okay, so F16, okay, the 16th Fibonacci number is 987. I didn't have to look up the 4th Fibonacci number, right? Because I have to square the subscript because these parentheses are around the subscript. So now what I have to do is take 987 and take it to the 6th power. 987 caret 6 equals what? Wow. one huge mother number. All right, so here's what it is in scientific notation. Probably see it on your calculator. 44914 8 6 2 times 10 to the 17th. So that would be the answer you would get. So remember, in this particular question, you had to square the subscript first. That makes it F16. You look up F16, that's 987, and you take it to the 6th power. And this is the sweetheart number you get. Decimal point would be 17 decimal places to the right. Okay, let's do question B here. Okay, for the Luca number, okay, if n is 6, it'll be the Luca number n, or sorry, 6 minus 2. That has to be squared. And then I'm going to take that to the 3rd power. Okay, so let's see. What is 6 minus 2? Again, it's 4. So I'm going to take the Luca 4. 4 squared is what? 16. And then I'm going to take that to the 3rd power. So Luca 16 cubed. All right, if I look at Luca number 16, it is 1364, right? And now I have to take it to the 3rd power. So 1364 in my calculator to the 3rd power, caret 3, enter, is 253771654. Now this number I actually probably can read. It looks like 2,537,716,544. So there you go. All right, folks, what we're going to do now is continue on with more work with prime factorization, okay? And we're going to work on some of the material that deals with trying to determine if a fairly large number is indeed prime or composite. So that'll be coming up. So just go to the next video and you'll be all set. Thanks for listening, and I'll talk with you soon.